What we're doing in this chapter is looking at polynomials. Up until now, we looked at linear equations, quadratic equations, and inequalities. Now the boundaries are removed. We're not limited on the size of functions we can use. We can evaluate. So if I gave you an equation, if I gave you a polynomial like this, and I asked you to graph it, what would you do? What do you need to graph a function? Okay. You need the x-intercepts. What else do you need? For any polynomial or just for this one? Learn something for everything that you're going to deal with. Why would you do a vertex for this one? It's a parabola, yes. And vertex, the rules we have for vertices only exist for this function. Anything higher than that, we won't be able to use the same rules. What else can you find out? What else do you need? Three more things, minimum. You need to know the y-intercept, the shape, and the direction of the graph. We're going to look for rough approximations because in order to find the exact graph, we have to have a whole bunch of points. So in this function, how do we find the x-intercepts? Or what's the general rule for any function? How do you find the x-intercepts? Set y equal to 0. Then what? How? See, that's the tough part because this is a pretty basic question. I'm going to give you some that are degree 7, degree 15, degree 30. So it's how we find the x-intercept. That's the tough part about this. So in this case, in this example, how would you do it? What's that? Are all terms like combined? Is x squared the same as x? Yeah, so all terms are separated. This can't go any further. Okay, what you're looking at is what method? You're going to move the 6 over. You're going to do what? What method are you going to look at there? That is one method for this type. That's one method. Again, this only works for quadratic equations. What you're looking at there is called the complete the square. And that only works for quadratic equations. We have to go away from that. We have to learn now how to find larger equations. So, no, but you're not wrong. It's just that it's one thing there. The first thing what you like to do is, can you factor this one? Why did I put two parentheses there? Two sets of parentheses. What do we know about this equation? We know the name of it. It's quite parabola. It's quadratic. What does that mean to us? It's symmetrical. Yes. What else? It's symmetrical about the no. It's symmetrical about what? The quadratic function has three possibilities. Close your computer. You don't need your computer. It's distracting you. It can look like this. It can look like this, or it can look like this. In other words, we can have two real solutions. We can have one real solution, or we can have no real solutions. Remember the connection. When we say solutions, what are we looking at? What are we talking about? Yeah, so the word solution is the same thing as x-intercepts, is the same thing as what we call factors. It's also the same thing as we call a zero. All of these relatively find the same location, the same point, the same number. And this is pretty important also. And we'll talk about that in a second. So let's go back to our question. So I know I have at most two possible solutions. So I put two factors in there, two parentheses. What goes inside them? When you factor a quadratic equation, you're always solving for that middle variable. So we're looking at x and x, because x times x equals x squared. The next thing you look at the second sign. If the second sign is a plus, that means the signs are the same. They're whatever the first sign is. So in this case, they're both positive. All right, they're both pluses. If it's a minus, then one's a positive, one's a negative. So the first thing, look at the middle term. Second, we look at the second sign. The third, we now have to find these numbers. The way we find those numbers is you multiply the first coefficient times the constant. So it's a times c. In this case, it's 1 times 6 equals 6. That's our target number. From here, we have to find two numbers that multiply to equal 6. That when we, in this case, so whatever the second sign is, then when we add them, we equal the middle number, right? In this case, yeah, 1 times 6, 1 plus 6. And since they're both the same signs, it doesn't matter where I put them. So these are my factors. Now what do I do? No, this is called the zero product principle. The zero product principle says this. If I have numbers that are multiplied together and they equal 0, if I have that, then what has to be true is the first term equals 0, or the second term equals 0, or they both equal 0. And since we don't know which one's which, we always opt for the last one. So since both of these together, this number times this number equals 0, what we have to do is take both of these and set them equal to 0. We have to find the x values. Those are the x-intercepts. So in this case, it's going to be -1 and -6. Those are my solutions. Because they're my solutions, they're also where the line crosses the x-axis. Now let's look at the difference between when I ask you to find the x-intercept versus where I ask you to find me the zeros of the equation. The x-intercepts are what? They're locations. So for this first one, the x-intercept is at -1, 0, and the second one is at -6, 0. Right. X equals -1 and x equals -6. The zeros are the specific x values that make the function equal 0. They represent the same number, the same location, same stuff, but they're written differently. X-intercept is a location, it's a point. The 0 is a value. So we know that at -1, we have an intercept. And then at -6, we have an intercept. Remember, our function was x squared plus 7x plus 6. We found the two x-intercepts. How do we know we're supposed to have 2? Because that's the largest exponent. The largest exponent is what we call the degree of the equation, of the polynomial. The degree tells us the maximum number of x-intercepts possible. Remember, the degree tells us the maximum number of x-intercepts. Since our degree is 2, we can have at most 2 intercepts, 1 intercept, or no intercepts. It all depends on what the rest of the function looks like. And And from this equation, what else is important? The plus 6. What does that tell us? What? Of what? Nope. What does the 6 represent? No. I know what you're trying to get to. That's what you're looking at, the axis of symmetry. No. What if all the x's were set to 0? What is that going to equal? 6. What is that called? If all the x's are 0, what's that number called? That's the y-intercept. The constant number is always the y-intercept. So we know in our graph here, 6, we know that we have a point on the y-axis at 6. Do we know any other points without doing any math? But it's not part of the graph. Quadratics are symmetric. You're right, around the axis of symmetry. So since they're symmetric, from this x-intercept, if I go over 1 and up 6, I got that point. I could do the same from the other end. Move over 1 and up 6, and I have another point of my graph. So I know the graph's going to look like this. Now we got to figure out what is that location there. What is the vertex? How do you find the vertex of a quadratic equation? To find the vertex, the V, we first have to look at this equation. What is that equation called? Have you seen it before? Yes, you would have if you would have been online for the last month. It's called the quadratic formula. It's used to find the solutions, or the solution, depending on how many solutions you have, of the function, of the quadratic function. Only works for quadratics. Notice there are only A, B, and C. There are no x's inside the equation. The x is on the outside. Only the coefficients. So what we have to do first is locate the coefficients. What is A? What is B? And C? 6. Let's go ahead and plug those in there. So it's negative b, which is negative 7, plus or minus 7 squared, 4 times 1 times 6, over 2 times 1. So it's negative 7 plus my inside the radical. 7 squared is 49. 4 times 1 is 4. 4 times 6 is 24. Over 2. Negative 7 plus or minus 49 minus 24 is 25. Square root of 25 is 5. Remember, these are finding my x-intercepts, my solutions. So now, once I get to this point, I got to take one of each side. So I have x equals negative 7 plus 5 over 2, and x equals negative 7 minus 5 over 2. Negative 7 plus 5 is negative 2 over 2, which is negative 1. Negative 7 minus 5 is negative 12 over 2, which gives us negative 6. So those are the same values we got when we factored it out. But it's got another use. The quadratic formula has another use. It actually has two uses. It's used to find the solutions, or the x values of the function. That's one thing it does. It also tells us the number of real solutions. Because it's quadratic, we know it has 2 automatically, at most 2. But with this function, we'll know exactly how many real solutions we're going to have. That's done by this part here. It's called the determinant. B squared minus 4ac, the determinant. It tells us if we're going to have 2, 1, or 0 real solutions. If b squared minus 4ac is positive, then 2 real solutions. If b squared minus 4ac equals 0, then we have 1 real solution. And if b squared minus 4AC is less than 0, then we have no real solutions. Can anybody guess why? Why do these three conditions exist? Well, let's look at it. Let's say, for example, if b squared minus 4ac equals 4. If it equals 4, then we have the square root of 4, which is, then we have the plus or minus 2. So we have a plus 2 and then minus 2. So that's two possibilities. If it equals 0, that number's gone. So all we have left is negative b over 2a, only gives us one solution. If it's negative, that means it's imaginary. Then we have no real solutions. It never crosses the x-axis. It's somewhere out in the ether. So that's pretty important in itself right there. We're interested in this one, the middle one. So if the inside equals 0, what's the square root of 0? 0. So what we have left is negative b over 2a. That's the graph that looks like this. It only touches at one point. So since we know what this number exists, this is the x value of the vertex, also called the axis of symmetry. So to find our vertex, remember, the vertex is a location. It's a point. Well, we know the x value of the vertex. And this x value is also the axis of symmetry. How do we find the y value? What's that? Exactly. Take whatever value you have there, plug it back into your equation. And whatever you get is your y value. That's your vertex. So far in this equation, we know the x-intercepts. The x-intercepts are at -1 and -6. We know the y-intercept is at 0, 6. So what's our vertex? To find the vertex, we have to find the x value first, which is negative b over 2a. -7 over 2 times 1, -7 over 2. That's what we're going to use. The actual location then is -3 1/2. And we kind of knew that already. How do we know that from our intercepts? Yep. Because since only works again, this only works for quadratic equations. Once you find the x-intercepts, the vertex is going to be halfway between them. So it's negative 1, 2. It's between -3 and -4, which is -3.5. So we know this is our axis of symmetry at -3x, -3.5, or -7/2. The actual vertex is at negative f of -7/2, which is -7/2 squared plus 7 times -7/2 plus 6. This finds our y value. Once I find my x value, I plug it inside the equation. So -7/2 squared. We look at the top number. -7 squared is what? Positive 49. And 2 squared is 4. We have positive 7/1 times -7/2. Positive times negative is a negative. Nothing cancels, so I multiply straight across. 7 times 7 is 49. 1 times 2 is 2, plus 6. Since we're dealing with fractions, it's 6/1. Now what we gotta do is how? Before you do that, you need what? You need common denominators. What is our common denominator? Yeah. The smallest number that all of the bottom one fits into is 4. The denominator cannot be smaller than the largest denominator. Because does 4 fit into 2? No. Does 4 fit into 1? No. But 2 fits into 4 and 1 fits into 4. So the LCD, the least common denominator, has to be at least as big as the biggest one you have. So the first one's already 49/4. The middle one, how do you get from 2 to 4? Multiply by 2, so top and bottom by 2. 49 times 2 is 98 over 4. And the last one, 1 times 4 is 4, so we multiply top and bottom by 4. So it's 24/4. Since I have all the same denominator, -49 plus 24 is 73 minus 98. 73 minus 98. 98 is bigger, so it's negative. 98 minus 73 is 25. So the y value is -25/4. So our vertex is at -7/2, -25/4. That's where our vertex is. We know that's correct because which quadrant is it in? It's in the third quadrant. And that's exactly what our picture says we're supposed to be. We're supposed to be in the third quadrant. That's great. but that's for quadratics only. Now, how do we graph our function? To graph our function, in our example, it was x squared plus 7x plus 6. First thing we did is we found our x-intercepts. Then we found our y-intercept. We found the fourth point. Right. The only thing we know by looking at this so far is it looks like this. And we know that there's supposed to be a vertex here somewhere. But we're going to have be exposed to some functions where it could look like this. The graph could look something like this. But we know by looking at what we did that it has to do this. So graphing any polynomial this is what a polynomial looks like. Yeah, because we're no longer be restricted to small equations. And believe it or not, you have it in your head already how to solve these. We just have to pull it out. You notice how it's always in decreasing order from the exponents. That's the first thing you have to make sure of. Whenever you get an equation, always make sure that the largest exponent is first and working its way down. So what does this number back here tell us? It's the constant. What does it tell us? On our graph. Right, this is our constant. But what does it represent in our graph? Very good. The y-intercept. Because if we set x equals 0, all of these disappear. We're stuck with a sub 0. These are the only two parts of the function of the polynomial that we are interested in. We're interested in the first one and the last one. This first one is called the leading term. The leading term tells us a lot, actually. What is the name of the exponent of the leading term? The degree. Very good. And again, the degree tells us maximum number of x-intercepts we have, solutions we have. The number in front is called the leading coefficient. The leading coefficient serves a little bit more duties here. It tells us the shape or and the direction of the graph. We've actually seen this already in chapter 2, section 5, the last one, the transformations. What are these 4 graphs going to look like? Notice the only thing I change is the leading coefficient. So what's the first one going to look like? Well, compared to our function, x squared. X squared is just like that. So what is this one? How is this one going to look compared to the original? Think what we did in chapter 2. Compressed horizontally or vertically. Anything outside the function is vertical. This is not inside the function, so it's vertical. It's an expression. So we're expanding. So what's going to happen here, instead of being this wide one, it's going to be narrow. The bigger the coefficient is, the skinnier it gets. What about this one? Negative 3x squared. What's that one going to look like? Flip upside down. It's going to look the same as the second one we just did, but it's going to be upside down now, but it's negative. The 1/3 x cubed, x squared. Remember, this is outside the function, so it's vertical. What happens here? Is it gonna stretch it or is it gonna shrink it? It's gonna shrink it. So it means here is it's gonna be wider. Right. Then the last one is just upside down. So you see the leading coefficient. The leading coefficient gives us the shape. Is it going to be wide or is it going to be narrow? And the direction. Does it go up or does it go down? This also works for what does x cubed look like? It's the lung S going up. But let's look at the same numbers. So what is this first one? 3x cubed going to look like? Well, yeah, I'm going to stretch it out. So it's going to be a lot skinnier. Negative 3x cubed. What's going to happen there? It's going to flip, but it's still going to be very, very skinny. And 1/3? Yeah, it's going to be much wider. And the negative makes it go the other direction. So far, so good. I did these two different types of graphs to show you a special comparison. The importance of leading term. Is something we called end behavior. The end behavior, what it does, it defines what happens on the outermost x-intercepts. What happens at the outermost x-intercepts are the solutions. And there are four things that can happen. We don't know what happens in the middle. These are the outermost x-intercepts. These solid dots. We don't know what happens in the middle. They can both go the same direction, up, or they can both go the same direction, down. It can be an increasing function, meaning as we go to the right, it goes higher, or it could be a decreasing function, and as we go to the right, it goes down. So in other words, the end behavior says the end of the graphs can either point the same direction or they can point opposite directions. What determines those? And all of this comes from this, the leading term. If our degree is even, they point the same direction. If our degree is odd, they point opposite directions. Where do we find the degree? The leading term, the exponent of the leading variable, right? So if n, the degree is even, we know that both ends point the same direction. If it's odd, it points opposite direction. But the leading term, if it's positive, then it's an increasing function. If the leading coefficient is positive and n is even, both ends point up. If it's odd, they point opposite, but the right hand goes up. If the leading coefficient is negative, then they point down. If it's even, it's a decreasing function if it's odd. This in itself is important. For example, in our previous example, yeah, we know that the degree is even and the coefficient is +1. So A is positive, N is even. So we know that once we found our two intercepts, that they have to point up. Again, this is rough sketching. To find the actual graph, we have to put some points. So let's look at some examples here. Sketch this graph. So what's your first step? What are you gonna do first? It's only got two terms, so what can we do? Can we factor anything out of there? Do they have anything in common? X cubed, very good. They both have three x's in common. If I take out three x's, what am I left with? Negative 2x plus 3. I just factor that out. So now what do? Now I take both of these and set them equal to 0. This will tell me the x-intercepts. So in the first one, to solve for x, I have to get rid of that cubed. How do I do that? Very good. Very good. By cube rooting both sides. So the cube root is 0, 0. And the other side, just solve for x. Yeah, I move the negative 2 to the other side, make it a positive, and then I divide by 2. X equals 3/2. These are my x-intercepts. So we have one at 0, and this is 1 1/2. What's my y-intercept? What's my y-intercept? It's going to be 0, because if I set x equals 0, it equals 0. So my y-intercept is also at the origin. Rule of thumb, if the x-intercept's at the origin, the y-intercept's at the origin. Okay, let's sketch the graph now. What do we know about this? Degree is 4, and a sub n is negative 2. They go the same direction down. So we know from the endpoints, the graph has to look like this. Because remember, all the end behavior, once we find all the x-intercepts, we just look at the outer two, and from there, our graph goes that direction. Now, what happens in the middle? Well, since it's a fourth order equation, if it was x squared, it looks like this. If it's x cubed, it looks like this. If it's x to the fourth, it looks like this. If it's x to the fifth, it'll look like this. Remember, the exponent tells us how many solutions we can have. So since this is a fourth order polynomial, degree 4, we know that something happens here that makes it look something like that. But we don't know what happens there. We have to find some points. But we know it doesn't cross the x-axis anymore between there. And that's why we have to plot a bunch of points. Let's see, next question. There it is. F of x equals 2x cubed plus x squared minus 8x minus 4. Sketch this one. I take it back. Quadratics weren't really the only ones we know how to factor. We can factor this one also. We've done that before. It's a cubic equation. Third degree. It's cubic. It's got 4 terms. The only thing at this point, only thing we can do to this equation by factoring by a method called grouping. What we're going to do here, what grouping says, is group them into 2 pairs. We put parentheses around the first pair and parentheses around the second pair. Okay, so put parentheses, the first 2 terms and the second 2 terms. What can we factor out of both of these parentheses? What can we factor out of, do they have anything in common in this first one? Yes, so we factor out an x squared in the first one, leaving us with what? +1, right? How about the second one? Yeah, since they're both negatives, we can take out a negative and a 4, which leaves us with what? Now, the easiest way to do this, whatever you factor out, to see what goes inside there, just divide those by what you factored out. So negative 8x over negative 4. The negatives cancel. 8 divided by 4 is 2x. Negative and negative cancel, makes it a positive. 4 divided by 4 is 1. That's the easiest way to figure out what goes inside there. Now, instead of having 4 terms, we now only have 2 terms. Factor again. What do they both have in common? They both have a 2x plus 1. If we take out the 2x plus 1 out of both of these, what are we left with? And that goes in the second parenthesis. How many solutions are we supposed to have? We're supposed to have 3. We only have 2. So can we do anything with this first one? No. It's as far as it goes. How about this one? Can we do anything with this one? It's safe to say yeah, because we need one more answer. So how do we factor that one? Nope. Well, yes, you could do that, but we're looking at it for this way. You're not wrong with what you said there. We could, because remember, at this point, we're supposed to set them equal to 0, but we can look at this. This is also called difference of two squares. Remember, x squared, 4 is 2 squared. Remember the difference of two square rule? A squared minus b squared equals a plus b, a minus b. That's the difference of two squares. Exactly. Because 2 and 2, x and x. Those are our three answers. So our x-intercepts are where? Take each of these and set them equal to 0. The shortcut for this one, whenever you have a coefficient in front of x, remember we did with the circles, it's always the opposite what's inside there. So this one is going to give us -2. This one's going to give us +2. This one, what's the opposite of +1? If you have a coefficient, it goes on the bottom. If you look at it, it's 2x plus 1 equals 0. Move that over and then divide by 2. So whenever you have a coefficient, that's always on the bottom. So those are my three x-intercepts. At -2, at 2, and at -1/2. Do I know any other points? Very good, very good. My y-intercept is at -4. What about the end behavior? Right, so it's an odd function. So it means opposite directions. Leading coefficient is positive, so it's an increasing function. So it goes from here and down there. So the graph is going to look like this. Now, at this, what you would have to do is, since we found the x-intercept, what you do is pick a point, plug it in there, see if it's positive or negative. If it's positive, you know the graph has to go up here. If it's negative, then it'd stay down here. But there's a shortcut to that. It's called multiplicities. X to the fourth minus 7x cubed plus 12x squared plus 4x minus 16. Okay, we can't do the grouping here because it's got too many terms. But at the end of this week, hopefully we'll get far enough so you can factor this out and then find me the x-intercepts. We know the y-intercept already is -16. So for right now, I'm going to give you the factors. And yeah, we should have 4 solutions because that's the degree is 4. They're both ends go up, right? So what are my x-intercepts? Yeah, -1, +2, +2, and +4. It's always the opposite of what's inside the parentheses. Any questions so far? And because our leading term is 1, leading coefficient is 1, it's positive, and n is 4, we know that our end behavior has to be going up. So our graph has to be going up at the ends. We also know that our y-intercept is -16. So our graph will look something like this. Yeah, we're W. But there's a more important thing to be noted here. Why didn't it cross there? Why did it only cross here and here? Why didn't it cross there? There's what? Ah, yes. Because if we looked at this and rewrote this, we have x plus 1, x minus 2 squared, x minus 4. Once we factor it, can you tell me the degree? If I just gave you that, can you tell me the degree of the equation? The degree, if you add those, because what this thing tells us is there's one x, there's two more x's, and there's another x. The degree is 4. These numbers here are called the multiplicities. It tells us how many times that answer repeats itself. But here's a more important thing about it. It tells us if the multiplicity is even, the graph bounces at that x-intercept. If the multiplicity is odd, the graph crosses at that x-intercept. So we could look at this thing and at the x-intercept of -1, because the multiplicity is odd, we know at -1, it has to cross. At +2, since it's 2, it's going to bounce. At +4, it's going to cross. That's a shortcut. Just by looking, you can tell me all that just by looking at the equation. There's something called the intermediate value theorem that tells us this. If we have a continuous function on an interval, So there is f of a, and here is f of b. This is what the intermediate value theorem says. If we're in some interval, f, a and b, if f of a and f of b have different signs, then there exists at least one x-intercept in the interval AB. Think about it. If it's continuous and this one is, let's say, a positive at 1, +5, and this one's at 5, -2, since the y values are different, that means it has to cross the x-axis somewhere. At least once. Doesn't tell us how many or where, it just tells us one that exists. Take another example. That'd be more than that. Yeah, I'll make one up then. Sketch this graph. Remember, to sketch it, what do you need to know? Do we know the x-intercepts? Yeah, they're already factored. So what are my x-intercepts? At -2, that's that one. This one is 1. -4. +4. And you're missing one. What about this one? It's an x, isn't it? Yeah, 0. Because how did you get -2 for this one? X plus 2 equals 0. In other words, once you factor it, set all of the factors equal to 0. X equals 0, x plus 2 equals 0, x minus 1, and then you solve them. That's where you get these x-intercepts from. So this one's at 0. So we should have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 solutions. So we forget now, what's our end behavior going to look like? So what is my degree and what is my leading coefficient? Is it positive or negative? Well, the leading coefficient is going to be positive or negative. Why? because none of the x's are negative. So this one's going to be greater than 0. What about the degree? Well, what's the number? It's what? 22. I think you're right. Add the exponents. And this is a 1. 3 plus 5 is 8. 6 plus 4, so it's 18, 19, 22. Very good. Very good. So what does it tell us about the end behavior? It's even and it's positive. So since that's true, both ends go up. Now we got to figure out, does the graph bounce or does it cross at those intercepts? At -5, what does it do? At -5, it crosses because it's odd. At -4, it bounces because it's an even degree multiplicity. At -2, it's 5. So it crosses because it's an odd multiplicity. It only bounces if the multiplicity is even. What does it do at 0? It crosses. At 1, it bounces. And at 4, it crosses. Of course, I mean, if I graphed it for you on a computer, it's probably going to be some stretched out thing because these are huge exponents. But that's pretty much how you, that's how you, it's easy to graph it that way. Much easier to graph it that way. It's much easier to graph it that way than what they're telling you to do in the book. What they tell you to do is once you find the x-intercepts, pick a number between those intercepts, plug it in there, see if it becomes positive or negative. If it's positive, then it goes up. If it's negative, it goes down. You have to do that to all of them. It's much easier if you do it this way. All right. That's it for today. What do y'all think?